Ever wonder how doctors spot tiny details in medical scans, like a lung nodule or a brain tumor? The answer lies in image quality. But even the best scans can be plagued by noise, those random distortions that make images blurry or unclear. Today, we're diving into a groundbreaking approach to clean up medical images using a technique called dual-path learning. Let's break it down. So what's the problem? Medical images from CT scans, MRIs, or retinal scans often contain noise. This noise can obscure critical details, making diagnosis harder. Traditional methods for removing noise usually target one type of image or one kind of noise, like Gaussian noise, which looks like static. But real-world medical images are messy. They might have multiple noise types, and they come in all shapes and sizes. That's where this new research steps in. The team behind this study created a massive, diverse dataset to test their approach. They combined images from 4 major medical imaging types: CT scans, MRIs, OCT retinal scans, and fundus eye scans. But here's the twist: they didn't just use real images. To make their model super robust, they added synthetic noise to create noisy versions of these images. Why? Because real-world paired data, where you have both a noisy and a clean image of the same scene, is rare. By generating noise themselves, they could control the experiment and test how well their model works under different conditions. Their dataset includes over 500 images per modality, except OCT, which had a bit fewer, ensuring the model isn't biased toward one type of image. They even sampled volumetric CT scans, taking 130 slices per patient to cover the entire chest. For MRIs, they included all common types, T1, T2, and flare, so the model could handle every variation. Now, how did they tackle the noise? Enter the dual-path learning framework. Think of it like having 2 experts working together. One identifies the noise, and the other reconstructs the clean image. The first path uses a neural network to estimate the noise in the image, subtracting it to create an intermediate clean version. The second path directly recovers the original scene from the noisy input. These 2 results are then merged in a fusion step, combining their strengths to produce the final, super clean image. The magic happens in the math. The model uses 3 loss functions to guide its learning: one for noise reduction, one for preserving context, and one for blending the 2 paths. It's like giving the model 3 different goals to hit, ensuring it doesn't miss the forest for the trees. The results? Let's talk numbers. Under Gaussian noise, the static-like noise, their model DPL outperformed state-of-the-art methods by huge margins. It boosted PSNR, think of it as a measure of image clarity, by 3.35% over a baseline model, 9% over red CNN, and a stunning 47.6% over BM3D, a classic denoising method. For fundus images, eye scans, the improvement was even more dramatic, 69.8% better than BM3D. While it didn't beat red CNN in all cases, it still crushed most traditional methods and showed strong performance across all imaging types. But numbers only tell part of the story. When you look at the images, DPL's results are noticeably sharper. Unlike other methods that either oversmooth details or leave noise intact, DPL strikes a balance, preserving fine structures while eliminating artifacts. This means radiologists could spot abnormalities faster and with greater confidence. So what's next? This research opens the door to more accurate diagnostic tools, especially in low-quality scans where noise is a major hurdle. By training models on diverse, synthetic data, scientists can develop robust solutions without relying on rare real-world pairs. Dual-path learning isn't just a step forward, it's a leap towards smarter, more reliable medical imaging. Thanks for watching. If you want to dive deeper into the math or see how this applies to other fields, hit that subscribe button. Stay curious and keep exploring the future of AI in healthcare.